We're going to continue our discussion today on how we do dependence analysis for control application. I'm hoping one of these upcoming weeks we'll be able to get a Realm speaker, but for the moment, this will be another Legion week. Okay, so last week the past 2 weeks we've been talking about control application, and today we're going to continue that discussion. We're going to dive into a little more of the details of how we do dependence analysis for control application. Let me try to page things back in for everyone. So before we were looking at effectively how we do dependence analysis, looking for mapping dependencies, across each of the different shards. And I'll remind you that, effectively every shard is doing the same dependence analysis on the same sequence of tasks that are launched with the same, projection region requirements and stuff like that. And the main thing that we're trying to infer, right, is the case where we need fences between two different shards, right, in your control replicated context. And what we want to look at today is how we actually infer the existence of those shards. We talked about it a little bit last week because effectively, let me jump over here to some of our slides. We're going to work through a very simple example here today and see how this maps back to the code. But effectively, imagine a case where you have very simple region tree. It's got a single partition, 2 subregions, and we're doing 2 index-based task launches. So the first one has 2 points, right? And each one of those points is going to use different subregion, and the second task is also going to use different subregions and have a different sharding function selected for it. Right, and you want to infer when you need fences between these 2 index-based task launches, right? And effectively, the point where you can align the fence is the case where all the dependencies between points in one shard align with all the points, or align with points in the other shard, and there's no cross-shard dependencies, right? But if you infer the existence of a cross-shard dependence, where a point task in one shard, might be either producing or consuming data from a point task from another index-based launch in a different shard, then you're going to need one of those fences, right? And so last week, we sort of talked about how that exists, in the case of opening and closing region trees and stuff like that. And Manolis made the accurate observation that if if you're switching region trees, we're pretty much always putting in those fences. We don't try to infer anything interesting, but if for the case where you're actually projecting from the same logical node in the region tree, now we actually have a more sophisticated analysis to try and infer whether it's safe to, align those fences between different index-based task launches, right? And that happens in this perform dependence checks function, which we've looked at many times before in the context of logical analysis. This is the function call that gets called on every node in the logical region tree as you're traversing it, effectively trying to find dependencies on prior tasks that we're using this particular logical node in the region tree. And most of this is pretty much invariant to control application, right? Except for this one part down here. Let's see, where'd it go? Right here. Where effectively, if you've inferred that, you can't prove that there's, effectively we do the normal checks on fields. If you're don't have overlapping fields, then you're independent, so you can skip that. Next, we check privileges. If everything is read-only, then you don't have to worry about, dependencies on tasks of the shards, because if both tasks are reading, then obviously there's no issues. But if you get that there's a true dependence, there's one more check that we can do to see whether we actually need a fence or not for control application cases, right? And that's the case where we have one of these shard projection trees, which we sort of touched on last week, but we're going to dive into a lot more detail today, right? And effectively, we can then, do a test to see whether whether these 2 different, index-based tasks actually have interfering shards between them, right? If they don't, then we just record a normal mapping dependence, right? And effectively, the first task launch will map its local points that are sharded to it, and then the second index-based task launch can map the points that are sharded to it, right? And the right thing will happen because there's no cross-shard dependencies. But if we fail this test, well, then we actually have to go and record close dependence between these 2 things to actually create one of those cross-shard fences, right, to make sure that effectively you get mapping dependencies hooked up across the shards, not just local to your particular shard, right? So today what we're going to do is we're actually going to dive into this has interfering shards function and actually see, in a real example, how it actually works in practice and the data structures that we actually use to make this work. So let's actually, we're going to dive into this. We sort of touched on this at the end of last lecture, but I figured we'd start here just to provide some context. And just keep in mind, like, these are two different tasks or two different operations that are both have projection region requirements projecting from the same, node in the region tree. And we're trying to infer whether those projection functions and sharding functions, actually have any cross-shard dependencies between the two tasks. So we're testing, the previous user versus our new user, right? And we're going to test these two, sort of projection function region requirements against each other to see which ones are interfering or not. So if we look at has interfering shards, we did this last week, but again, I'll just make it, very, very clear what's happening. Right, here's has interfering shards. We looked at this very quickly last week. Effectively, if the two are the same, projection functions and sharding functions and stuff like that, then we know we can align it because we know they're going to have, effectively the same kinds of same sets of point tasks mapped to the same shards and stuff, and everything should work out pretty nicely. If that doesn't work, then we have a cache of these tests that we've done before. And if we can find our entry in the cache, effectively we can return the result of like the test that we did previously. So that's what's happening here. There's effectively a cache on this computation because, it's often the case that applications are reusing their projection functions and sharding functions and stuff. And so, it's likely the case that if we've, done this analysis before, we'll end up needing to do it again. And so we do maintain a small cache here. And if we hit it, then great, we don't need to do anything else, and we can move on. But, in the first time you go through the loop or whatever, the first time your application launches any projection region requirements or with different sharding functions and stuff, then you actually have to do the test, right? And so what we'll look at today is how this has interfering shards test actually works. So we can actually, you'll notice this broadcast or dispatches to the context object. So effectively you're going back to your parent context. You want to do this because you may need to do an exchange of information across the shards to help determine whether all the shards agree that, whether a fence is needed or not. So let's actually take a quick look at that, and then we'll actually look at how this test works. So we search for has interfering shards. The normal inner context one is pretty simple. It just tests one of these data structures, these projection summaries against each other. But that's not actually the case we're interested in today. We're actually in a control replicated context. So we need the control replicated version of this. So in a replicated context, effectively we're going to do the test locally, and we'll take a look at this test. We're going to dive into it in more detail. But effectively we're going to see whether, this local shard thinks that a fence is needed. And then, we do an all reduce across all the shards to see whether any of the shards think that a fence is needed. And if any of them think a fence is needed, then we automatically put in the fence across all of them. Right, and so effectively, this all reduce collective here is effectively just making sure it's just doing an all reduce of the local result to see if any of the shards thought that they needed a fence to be inserted based on their analysis of their local points in this data structure. And you'll see why this all reduce is needed by the end today. And this sync all reduce, just gets you the result of this this Boolean result across all of the shards. So what we want to look at today is effectively this interferes test, because this is actually the thing that determines whether effectively a point task on or whether your local shard thinks that there's an interference between these two different projection summaries. And so we're going to dive in today is effectively the data structure that we use to test these two projection summaries against each other in a real example, and we'll actually then go look at how that actually maps to the code. So let me switch back over here to this example here. So we're gonna do this sort of example for three different programs. So you can think of each one of these three things as a different program. There's two index-based task launches here, T1 and T2, right? In the first index-based task launch, effectively in this first example, right, point task 0 is going to map to region R0, and point task 1 is going to map to region R1. The same thing for point 0 and R1. And then we're going to shard each of these to a different shard. So maybe I should have used like a different syntax here. Right, make it clear that point zeros are going to shard 0 in this first example, and point 1s are going to shard 1s in the second index-based task launch. And what Legion is going to do in this projection summary class is actually make a little data structure of the, effectively the subpart of this region tree that each of these point tasks, or at least the local points that are sharded to each of these shards, are going to use. I'll tie this back to the actual code here in just a minute, but let me describe what these data structures look like. So in shard 0 here, right, effectively for T1, it's going to make a picture or make a data structure that represents the sub part of the tree that that T1 is actually using, right? And what it does is it records that effectively that it's using it's projecting from this partition, right, and it's using this particular subregion here, right, and records that shard 0 is actually using this subregion here. Our local shard is using R0, but it also records that there's some other children or some other shards that are using this other child over here, R1, of this particular partition. We actually don't care which shard is using R1. We just need to care that there exists a shard over here that's using R1. And similarly, for T1, shard 1 is going to make a similar data structure. Effectively, it's going to make a data structure that represents the part of the tree that its point tasks are using. So point 1 is using region R1, so it records its shard 1 is using this particular subregion, and then it records that some other shard, in this particular case shard 0, is actually using this child R0 off of here. But we don't actually need to represent that explicitly. We just need to care that effectively there is some other shard over there that's using one of our children here, right? And then we do the same thing for T2, right? Effectively, we make a similar data structure. In this particular case, T2 is using the same regions and shards, so this all looks like very similar to T1, right? And then what we can do, right, is effectively using this information, we can actually test, right, like whether there are interfering, we can test each of our point tasks. We can effectively in shard 0 we can test this particular projection tree. I'll call this a projection tree, against the projection tree that we know of for T2, and see if there's any interferences. And let's assume that this partition here is disjoint for the purposes of this example, right? And so in this particular case, shard 0 looks at these two data structures that it knows about, right, and says, okay, great. So I know that there are other children over here using R1, but this partition is disjoint. So all of my users down here for T2 are going to be non-overlapping with any of the children that are using children over here. And similarly, like if I had to handle anti-dependencies, right, like effectively this R0 here is also going to be non-interfering with any shard children over here being used by R1. And so therefore, I don't think my local shard concludes that I don't need to have any dependencies or require a fence with anybody else in this projection region requirement. And independently, shard 1 is going to do the same analysis, right? Effectively, it's going to look at its shard users here and say, obviously this guy, I'm going to need R1 here, and this previous task need R1 here, right? But this partition is disjoint, so R1 is not going to interfere with any of these shard children over here in R0. Similarly, this for anti-dependencies, this R1 here, the shard user over here is not going to interfere with anything that's using other children over here in T2. Right, and so therefore I don't need any dependencies, right? With other point tasks, mapped to remote shards, right? And so then they do this all reduce between themselves, and they can conclude that effectively no fence is required between them in this particular example of the program. So before I go on and do the next example, does this make sense? Like effectively, each of the shards have a local data structure that represents, sort of the stuff that they're using, as well as some knowledge of, whether there are other children in this projection tree that, are used by other shards. And it uses that to determine whether or not, there's any interferences, from local points to remote shards. Because like the next example will make this a little more interesting. So. Okay, I'm going to assume in the absence of questions I can move on and rearrange this picture to make it look different for this next program over here. Okay, so let's do this next program because now things are going to start getting more interesting. Okay, so in this next particular example, right, what I'm going to do is actually switch the sharding function. So I'm going to maintain the same projection function, for each of these two tasks, right? They're each going to project to R0 and R1 respectively, right? It's pretty much the identity projection function. But I'm going to switch the sharding function on T2, right? So it effectively it shards point 0 is going to go to shard 1, right? And point 1 is going to go to shard 0, right? And so what that's effectively going to do is, these projection trees are now going to look a little different for each of these different cases, right? So effectively, let's see here. So, T2 now, right, effectively is going to let's see. It's effectively what we need to do is actually swap these two data structures here. So let's pull this one over here. Let's grab that right there also. Right, because you can see that shard 0, right, is now getting 0.1, right, which maps to R1. Right, it's going to record shard 0 over there. And if I move this stuff up here, right, and this is going to map to shard 1 here, right? And so effectively, what that does, right, is effectively these are what the projection trees will look like, for the second program over here, right? So for T2 here now we've got, effectively, a different subregion being used by shard 0, right? And different children being used over here, in the subtree over here, right? Used by different shards and vice versa. Right, so now if we actually do the test to ask the question locally, like in shard 0, is it the case that effectively, can I conclude that, that I can actually do all of my analysis locally, or is it going to be the case that I might have alternative users and other shards that might need some of my the data that my point tasks are producing or consuming, locally, right? In this particular case, like, if you test R0 over here, this point task here, it may produce some data on shard 0 here. And then we look at T2 and we look at, there's some other shard, that's going to be using R0 from this partition. We don't know which shard it is, but we know that there's at least one other shard that's going to need data from R0 that's produced by this T1, by the point task over here, right? And so therefore, shard 0 is going to conclude that it needs a fence. Right, and similarly, shard 1 over here is going to look at, it produces maybe some data over here in R1, right, and then it goes to analyze T2, and it looks at this projection tree here and says, oh, there's some other, child shards down here, using R1. We don't know who they are, but somebody's going to need it, and therefore, effectively, it's going to need to go, or it's going to require a fence between these two tasks, to make sure the mapping dependencies get hooked up correctly. Right, and then you do the overuse. They both determine that they needed, a fence, and therefore, you get a fence between all of them. Right. So this, and that's accurate in this case because effectively, these R1 to R1 dependencies, exist on different shards, and therefore, you actually need, a fence between the shards to make sure that those mapping dependencies are happen in the right order. Okay. Does that make some sense to folks as to how these data structures changed, in relationship to this program and the change in the sharding functions? Even though the projection functions stayed the same, the change in the sharding functions changed the shape of these data structures to make it so that Legion could actually, infer that a fence is needed between the different shards for hooking up mapping dependencies.
So we would get one fence, right?
One fence, yes.
Correct.
Yeah.
And if they were read-only, we would get no fence.
Yes. So in the first example, we get no fence, and in this particular case, we get a fence between T1 and T2, right? It applies.
Even in the second example, if T1 wasn't producing, we would not get a fence, right?
If T1 was not producing, you mean
read only? I mean.
Oh yeah. So again, coming back to this code, if both of these tasks are read only, right, then that would have gotten handled above this test, right? Let me actually jump back to the code. Where was it? Right, so like, when testing the two users against each other, the first thing we do is we actually check for field independence, right, checking to see if there's overlapping fields, right, and if there's overlapping fields, the next thing we do is we test their privileges, right? And so if they were both read-only, we would have gotten one of these Legion no dependence cases, and so we wouldn't even have made it into the code down here to test for the more sophisticated, interference test. So effectively, if both of these were read-only, we would have previously concluded that we wouldn't even need to do this test, right? So at least one of these has to be a writer or a reducer or something like that.
And the first time we figured out in the second example, of course, the first time we figured out that we need a fence, we won't do any further checks, right?
Yes. Yeah, effectively, it's not necessary. I mean, the nice thing about these fences is that effectively Legionist doesn't hook up precise point-to-point dependencies in this case, right? Effectively, we just determine whether a fence is needed between all the points in one index space and all the points in the next index space.
And that should be enough.
And that's enough, right? It's, again, we can be imprecise in the mapping dependence because like the physical analysis will eventually be precise. So like we don't bother figuring out which point tasks are going to interfere with each other across these two index space task launches. We just conclude that there is some interference that we have to deal with, right? Yeah. And that's actually going to be important to making sure that these data structures don't get overly large. There's going to be some tricks involved with that. So we'll talk about that a little bit later.
Makes sense.
Okay. All right. Let's do the third example, and then I'm going to go talk through how these data structures that I'm describing actually map to the code. Okay. So in the third example, in this particular case, what I'm going to do is actually I'm going to keep the sharding function the same as the first one. Effectively, point 0 always shards to shard 0, and point 1 always shards to shard 1. That's true down here also. But I'm going to switch the projection function, right? So effectively, point 0 maps to R0 here, but, and for T2, point 0 will map to R1, and point 1 will map to R0, right? And now this will actually look a little bit different. In fact, what we're actually going to do is go back. Let's see here. Let's make sure that I'm... So actually, this is correct. Let's see here. Make sure I'm doing this right. Yep. Make sure that I give you the right example here. I hope I didn't mix these up in my head. So point 0 maps to R1. So I actually think that I switched these examples. I think that I did this example with this particular picture. Let's see here. So actually, no. So the one thing that changes here is that I did this right. So point 0 maps to R1 on shard 0. Yep. So actually, I think what you get is the same picture here. It's just that, so you actually get the same picture here, but for a different reason, right? Effectively, we switched the projection function and the sharding function between these two examples. So you actually get the same picture here. Right? Effectively, what we did was we moved the projection function back to being, mapping R1 to shard 0, which is exactly what's happening here, right? And the same thing over here, right? And so I guess, you get the same data structures here as you get in this example, right? But effectively, the reason for that is because we switched both the projection and the sharding function. We swapped both of them at the same time, and so you get the same picture. And you actually get the same analysis between both of them. Does that make sense? Right, and just to confirm that, let me just talk through what happens here, right? Like, point 0 is mapping to R1 in shard 0, so you can see this data structure here, right? Like, effectively, we're using R1, shard 0 is using R1 on shard 0 from what we know, and then, there's some other, point out there that's using R0, which is going to be shard 1 over here. And similarly over here, right, point 1 is mapping to R0 over here and recording that shard 1 is using it. And then, there's some children over here for this projection or for this partition being used by a different shard. In this case, shard 0 is using R1. So you get the same picture, and the same analysis applies. The same data structures exist, and the same analysis gets done between these two index-based task launches. And again, you're going to conclude that you need a fence here. Okay, does that make some sense? Hopefully. Okay. Let's actually look at some code for some of this stuff. But I want you guys to have these pictures in your mind that like effectively what's going to happen is each of the projection summaries is going to have a local projection tree, and when we say a projection tree, it's going to be this sub piece of the region tree that's being used by the local points, that are already sharded to this particular shard from an index-based task launch. But at the same time, we're going to record, if there are children in other parts of the tree that are being used by other shards, right? We'll have some representation of that in our data structure, and we can use that for testing for dependencies on other shards that might exist between our local point tasks, that we know about in this projection tree. Okay, let's go look at some code. Let's see. Let's take a look at legion analysis first here. Right. Let's actually look at projection summary first. We looked at this briefly last week, but I'll just remind everybody. This is the projection summary class, which effectively summarizes these projection region requirements. Right. Effectively, it has an index-based domain, right? A projection function, a sharding function, a sharding domain, some projection arguments. These are all things that get passed in by the user from the application side. Right, and we sort of remember, each of these, and for any, if an application reuses, a projection region requirement with these same properties, we can reuse the same projection summary. Right, and the important thing that you've got here is this projection tree. This projection tree, this is a pointer to a data structure that represents these, sort of subtrees of the region, representations of subparts of the region tree that are being used by point tasks, in our local node. Right, so this tree right here is exactly the pointer to one of these projection nodes are going to be nodes in that tree data structure that represent subparts of the region tree. This projection region requirement is actually using. The rest of the stuff down here is all helping our properties of this projection summary. Is it the case that all the subregions are disjoint? Do they represent using a complete subtree? Does it permit this name-based self-analysis? Let's say it's something that will be useful for cases where we want to prove point-to-point dependencies in a different case, and whether each region in this projection subtree has a unique set of shard users. These are properties of this projection tree that we're going to effectively summarize that'll help us with our analysis a little later. And this exchange right here helps us to know when the construction of this tree is done. We'll talk a little bit later about how that construction is done, but let's for now just assume that this projection node is, this tree is constructed, and we've got it, on each of our shards, so we can actually test it against each other. If we go look at this projection node class, we'll actually see it is a virtual base class. There are some virtual methods on here that you need to define. You can see a bunch of virtual methods down here. And in particular, there's going to be two instantiations of this projection node class. There'll be one for region nodes and one for projection nodes, right? So there's a projection region, which inherits from projection node, and there is also a projection partition, that also inherits from projection node. And so those represent, these different nodes in the region tree, right? So you'd have a projection partition here, for this node, and then a projection region for this node, projection partition, and projection region. You guys get the idea. So that projection node summary that projection node pointer in a projection summary just points to the root, of this tree, and then you've got sort of a subtree corresponding to each of the use cases, or corresponding to or I should say it points to the root, and then you've got a whole subtree below it of all the users for this particular projection region requirement on this local shard. Okay. Let's go back to projection node. Projection node has exactly one member variable in it, and it's a very important one. And you can see that this it has this shard children member variable. Now, and you can see we've actually listed the shard children here, right? And you actually have this on every node in this projection tree, right? So there's actually a shard children for like this child here. It's just that it'll be empty, right, for this node here because there are no users below here, right? But effectively every one of these children, or every one of the nodes in this projection tree here, effectively have one of these shard children interval trees to store the names of children in the region tree that effectively have shards that are using them. Now, a very important property there's two really important properties of this interval, or of this shard children data structure here. Let's see. The first one is it doesn't actually encode, which shards are using those children, right? So we don't actually need to materialize the subtree down here that, is being used by other shards, right? Effectively, we're not materializing, R1 over here or R0 over here. We're just recording that something is used, some other shard down there is using it, right? And we don't even record which shard. We just need to know that some shard somewhere else in our index-based task launch is using, children in that subtree, and we'll use that, effectively to encode, to realize that, there's some other shard that might be interfering with, say, some of our point tasks that are using something else in like a different index-based task launch. Now, the other important property of this is that this interval tree actually uses a very clever scheme for encoding the names of children that are being used, in that particular subtree. And what the interval tree actually does is actually stores, effectively ranges of children, ranges of the names of children that are actually being used, right? So here in this picture, I've actually said we label R1. What this interval tree actually stores is it actually stores ranges of the names of children. So like imagine a case where this partition was actually like, a very large disjoint partition, right? Where like you might actually have like thousands of subregions in this partition. Like maybe you have a disjoint, partition that spans your entire machine, and it describes subregions where each of the subregions are going to correspond to data needed by like each of your GPUs, right? In like a machine with like 10,000 GPUs, right? So in that case, right, you don't actually want to enumerate the names of all these children, right? Instead, what you want to encode are, you want to have some nice encoding of the names of subregions that are being used in that particular partition. And this is a property of Legion's, the way that Legion actually, this is actually, a detail, but it's an important one, is that Legion, like let's say this partition was like maybe a 2D, had a 2D color space, right? That, actually was like sparse or something like that. Legion actually has a mapping from like, the color space for this partition into a dense or roughly dense 1D space of Legion colors, to name the children in this partition. And because of that, we can actually encode dense ranges of children in this particular subtree very, very efficiently, right? You can effectively encode it in space that is much, much less than the number of children in this partition. And I'm not going to talk. I won't show you the code for this today, but I'll sort of hint at what happens. Legion effectively tiles the color space for this particular partition with sort of a z-order curve to effectively come up with a really dense encoding of the points in this particular color space. And it will try to compress that into as small a space as possible. And in the case where you've got like sparsity in your color space, we even will like densely tile the rectangles in your color space and stuff like that, such that we create a dense encoding of the names of the children in this partition. And therefore this interval tree data structure actually does really good at compressing the names of children that are being used by different shards. And you can do tests really efficiently to see whether any shard, might be interfering with, with the children that you might be needing, down here. So like, in the case where you've got a child that's being used locally, you can test against this interval tree whether there's any shards up here that are also using the same subtree very, very efficiently. And that's really important because what that's going to mean is that this data structure here, right, the names of these interval tree children, right, will never be as big as the the number of children actually being represented, right? We don't want any data structures here that are going to be the same as the size of the machine that we're actually running on, right? So like even if this partition has a number of subregions that are the size of the machine that you're running on, we don't want our local shard data structures to ever be that big, right? And by ensuring that we encode it in this way, we make sure that effectively we never have data structures for any one of our shards that's as big as anything that's as big as the whole machine, or as big as the number of shards or number of partitions or anything like that. And so that's a very, very important property that we maintain in this data structure. Okay, let's actually take a look down here. Okay, so now let's actually take a look at, we've got projection regions and projection partitions as well. In particular, if we look at projection regions, we also see that they have some more member data structures down here, right? So projection regions actually will encode, the names of each one of these data structures, I should say, actually encode names of local children. So local children are children below us in the subtree that are actually, have users from the local shard, right? And so there, it's okay to actually encode, an explicit representation of the subtree, right? We actually need to know the pointers to the sub things in our local, region, or I should say, we actually have local children here for partitions, right? Because there, that's stuff that's local points that are sharded to our local shard. So that's only point tasks that are local to us, and therefore, that'll never be as big as, potentially the size of the machine, unless the user has used like a particularly bad sharding function that actually like shards everything to one shard, right? Like, and hopefully they don't do that, right? But at least like the user has some control over that part of things, and so we actually track the names of local children. So if this region tree were actually like more than one level deep, or more than one partition level deep, right, had other partitions down here, some of these regions might have pointers to other local nodes in these local projection tree data structures. Okay, and then effectively what we've got here, in projection region, we also have the list of the names of other shards that are using this particular region in the region tree, right? So effectively, these are point tasks that have mapped to this this local node in this particular tree, and this handles the case. You see shard ID, and obviously in our particular example here, our shard users are all things that are local to our particular case. But you could also have cases where like multiple points from the same index-based task launch could have multiple points that map to the same region with different shards, right? And you actually want to encode that to detect cases where you've actually got like point-to-point dependencies, without needing to like determine that there's some interfering child based on a partition or something like that. You might actually get multiple users from different shards using, say, R0, right? In which case, I could have done something where like maybe this task did R0 and R1 here, but then we had some example like maybe I could do something like this where this task T2 is reading, and we've got like both points mapping to R0 on different shards, both reading R0 from this this T1 producer, right? And R1 is just ignored, right? In which case now you'd have multiple point tasks being sharded to different shards, but both using R0, and so you need to be able to detect cases like that. And so this actually handles the case where you might actually have multiple shards or multiple points from different shards mapping to the same logical region, which can happen with like read-only tasks and stuff like that. And if we look at projection partitions, right? Effectively, there's a little bit there's some extra help here for doing name-based dependence analysis. We're not going to talk about that today. That helps with finding point-wise dependencies, which something the Lié team has asked us to start doing in the future. So that's sort of an optimization we're doing here. But in general, the main thing we just have here are the list of local children in our partition that have subtrees for our local partition. That have point tasks that are being used below us in the region tree. Okay, let's actually, now, so I sort of showed you what these data structures look like. You can actually map these pictures here over to, these data structures, these projection node data structures. Let's actually see how they're actually used to do this interference test, right? So over here, I showed you like this. This is the test for has interfering shards on two projection summaries, right? And you can see, this test is effectively a fairly simple thing. It gets the two projection trees from each of the two summaries, right? And it does this interference test and tells us which shard we're on when we're doing this local test. So we can actually go look at this interferes method. This is a virtual method on each of the projection node classes. So we'll jump over to Legion analysis here, and we can look at we'll do projection region has interference first. So, right, effectively, actually, it actually tests interferers first, so let me show you the right method. There's a little bit of a dispatch here. right? So projection region, this is actually the method I called from the replicated context, right? Here's our other projection node and our local shard ID. We assert that this better be a projection region also. We should be zipping. Effectively, what it's doing is it's zipping these two, or I should say, it's actually zipping these two data structures here in the same shard. So effectively, we both start at these two partitions, and then we go to each of these two regions. So maybe I should start with the partition nodes. But you're effectively zipping these two data structures, and the only reason you can zip these, sort of walking from the same nodes in the tree, is that we know both of these are projecting from the same root node, right? We both know that they're projecting from the same partition, right? That's kind of guaranteed by the higher level code that ensures that, effectively each of the projections that we're testing against each other are projecting from the same node in the region tree. And so let's actually start with partitions, since this example starts with partitions. Okay, let me go to the right method here. Let's see, projection partition interferes, right? Again, testing against another projection node. This better be a projection partition. In debug mode, we'll do a little dynamic cast to confirm that. Otherwise, we just kind of assume it and do a static cast, and we call this has interference method. So if we look for projection partition has interference, okay. There are two cases here, right? Effectively, this test will depend on whether this partition is a disjoint or an alias partition, right? So in the case where this is a disjoint partition, right, which is effectively the case that we are in this particular example, this is a disjoint partition, right? What we can do is we can iterate over, all of our local children, right? Check to see if there are any other children in the other in the other node, right, effectively, and then traverse over each of them to see whether they have, an interfering, or whether they have an interfering children, right? If we don't have it, then we test for, whether, well, actually, there are two cases here, right? There's a case where it doesn't have the same child as us, right? In which case we're going to test the shard children to see whether it has a child that, is the same as us, right? And if it does, then that's going to be, an issue that we're going to need to have an interference, right? And that's effectively, what's happening here, right? Effectively, like, you're testing, we know that we're in shard, let's say we're over here in shard T2. We know that we've got a local child here in R1. We need to test, against the other projection tree to see if anyone else is using shard1, because there's no local child for R1 over here, right? But we're going to test in the shard children to see whether it has a corresponding one. And when we find that it does, right, then we're going to return true, because effectively that implies that, there is some other shard somewhere that's using, something else in the tree down below, which is potentially interfering with us that we don't know about. If it does have the same node, then we can actually traverse, down that subtree and actually look for interferences down in that subtree, right? And that's a recursive process. So that'll effectively zip, two region nodes together, for further down the subtree, right? So we can go test that. And then we also have to do the check in the opposite direction, right? Effectively, it does the same thing. So you have to test to see whether there's any interferences on children in that direction as well. Right, so that's the case for disjoint. Alias is actually a little bit different, right? Effectively, what you really need to do is just check to see, are there any shard children that are not empty, right? If there are, then you need to check that either they're all the same, right? In which case we can zip down the interference path, right? But if not, well, let's see. If we have different numbers of interfering children, well then, yeah, they're definitely going to be interfering, because there'll be at least some child that doesn't overlap. But if they're all exactly the same, then we can actually test them against each other, test each other's children against each other, and see if they have interferences, right? And if they actually don't, then we can return false. But most commonly, they probably one of them does have an interference, and so we'll go take a look at that. So that's the projection partition interference, and you can see there's also the region version, right, which we looked at just a moment ago. Oh, projection region. Yeah. Interferes, right? And again, this also better be a projection region, otherwise, we've done something very wrong. And so we can actually test that for has interference, right? So this is the test on actual logical regions, right? And so the first thing we can check are whether the shard users are the same, right? if either one has more than one shard user, right, then effectively, they're almost guaranteed to be, they are guaranteed to be interfering, because like then we're gonna have multiple shards using the same region in the region tree, and so therefore we're gonna need a dependence between them, right? Let's see. If our shard users are empty or not empty, and the last one is our local shard, right, or not our local shard, then definitely there's going to be an interference, right? Effectively, we're only going to be able to avoid a dependence if like they're both users are our local shard. So that's testing that for both of those cases. In this case, either we have all of our users are our local shard, right? Or and then we have to test to see if there's any like local children like further down the projection tree that we need to go test against, right? And so this is handling the case where we actually have to do the traversal, to recurse down the tree. And if you get all the way down here, then you actually haven't found any interferences, right? And so if I actually like were to like, let's actually go back to how this picture looked, at the beginning, right? Effectively, like, just to show you this path going down here, right? Effectively, if we were testing, this is the program up here, right? Effectively, where these two things are the same, and we're on both of these. We're testing these two nodes against each other in the shard tree, right? We're on the same node. We've got the same shard users, right? So effectively, you can see here, the shard users are both of size 1, right? So we can skip this pass. We don't need to hit this, right? If we look at the shard users on our local one, right, there's exactly one, and it's our local shard, so we're good here. Similarly, if you look at this one, effectively looking at the other node shard users, right, it's exactly size 1, and it's also our local shard, so we're still good there, right? And then if we look at, we don't have any shard children, so we're good there, right? And since we don't have any the sizes of the local shard children are the same, they're both 0. Right, we do the tests, right, there's no local children to iterate over, so we don't need to go through this loop, and therefore we can conclude that, effectively there are no local shard dependencies between these two nodes on each of those two data structures, right? And that's how we're actually able to prove that no fence is required here, because that analysis happens the same over here on shard 1, and then they do their all reduce, right, and effectively they can prove that, there's no interferences between them. Okay, so effectively, that's how this has interference test works on these projection nodes, right? And so if I'm just popping back up the stack here a little bit, right? Like effectively, you do that recursive test across each of those two projection trees on each shard, right? And then they do an all reduce of the results across the shards to see if any of them recorded the need for a fence, right? And if any of them did, then you can conclude that you actually do need that particular fence across the shards. Right, and again, this all pops up, back here, to this has interfering shards test, right, which effectively is making sure that it is testing for whether these two index space, tasks actually did need a fence, and if they conclude they did, then we record that we do need a fence here between them up here at this top level logical analysis. Okay, so I think. I'm going to stop and let you guys ask questions, and if nobody has any, I'm probably going to stop here today, because this is sort of the crucial idea here, and I don't want to talk about how this data structure how these projection tree data structures get constructed quite yet, because like that'll probably be a whole nother lecture, but effectively, I want you to see how they're used first before to understand, what their semantics are and what the data is that they need for testing these interferences between two index-based projection tests. Okay, so any questions for today?
Why would we need the all reduce? All the shards that are participating are doing the same analysis, right?
They are, but the data structures are not actually the same across all the shards. So I don't have an example of this here today that I can show you, but effectively there are cases, because of the nature of these projection trees, right, it's possible for some of the shards to see that they might have interferences with other shards, while other shards will conclude that they don't have interferences with anybody else. And because of that asymmetry, you need the all reduce in order to make sure that they all come to the same conclusion to insert the fence or not. because the fence is kind of a a cross shard thing, and so therefore all the shards need to agree that they're going to do it or not. Um, so
Could you go back to the place where we are doing the all reduce? Because I
yeah,
just wanted to see like where do at which point are we do that?
let's see. Here you go. Yep. Right. So effectively, you do
So
the local test.
we have a all reduce in for every case, or
Yeah. So effectively, you do the local test, right? Effectively, each shard does its test of its projection tree against the other projection, the projection tree, the two projection trees for the two index-based task launches, right? So they each do their local analysis and decide based on their two projection trees that they can see, do they need to have a cross shard fence or not, right? And then you do the all reduce across all the shards to say whether they all concluded the same thing or not. Right, and if any of them concluded they need a fence, then they're all going to do the fence.
so does this mean that when we are performing logical analysis on index-based tasks, we are all reducing after every step?
Not often because you're going to hit in the cache pretty frequently. Like, oh, where did my cache go?
Okay.
Right,
Okay, so
like
that we have
the
like a other route. Okay.
let's see, where did it go? What was it called? Hang on. Back to the region tree. It's called has interfering shards. Right, so like these projection summaries, they can actually deduplicate across index-based tasks launch, right? Like you can have the same. The projection summary just encodes like the index space of the task launch, the projection function, the sharding function, and a few other parameters. But if the same index-based task launches have those same parameters, they will reuse the same projection summary. Right, and then we've got a cache of the tests of these projection summaries against each other that we hit in pretty frequently. It's very infrequent for an application to actually be like creating new sharding functions and projection functions every single iteration. Like nobody really does that. Yeah, and so we hit in this cache more often than not. So you do have to do the all reduce the first time you see like a test between two projection summaries, right? That you haven't done before. But effectively, once you've done that all reduce, then the next time you see it, you already know the answer, and you're not going to need to require that all reduce between them.
Right. I mean, it's not really apparent because in the like the diagram that we have, we do record like shard children's, right?
Record shard what?
We record like the shard children, right? Like the children of
We do.
other shard thing. Yeah, so that kind of was telling me that we have all the nodes, all the shards have the information, and they wouldn't need to like communicate. But maybe in more complex cases.
Well, yeah. So, and they are going to need to communicate to also construct these projection summaries. So the first time you see a combination of an index-based projection function, sharding function, triple, it's actually a few more parameters than that. But the first time you see that, you do actually have to do a little bit of communication to actually get these shard children. So you're right. Like actually computing these shard children does require a little bit of communication to actually construct these data structures, and that's what we're going to look at next time. But again, like effectively, you can reuse the projection summaries. If you see another task launch that has the same index-based domain and the same projection function, the same sharding function, even if the task name is different, you can reuse the projection summary because it's a property of those projection functions and sharding functions and stuff like that, right? And therefore you don't need to like recompute things. So sorry, you don't need to recompute the projection trees, right? You can reuse them. So,
right.
Yep.
Makes sense.
Yeah, so we will look at how the projection trees get built the next time because that is another important part of this. But I want you to understand the need for the like these projection for these projection trees in the first place. Yeah. But I think just coming back to your original question, I'll kind of leave this as an exercise for you guys to think about, and if you can't figure it out, let me know. But there are ways to construct projection trees where effectively some shards will conclude that they have interferences with other shards, while other shards may conclude that they don't have any interferences with any of the other shards. And so it's not a symmetric thing, right? It's not
Even
like
even though, yeah, that's where I got confused. Even though we are recording like these children's,
mhm.
it still would result in a asymmetric tree.
Yes. So you'll need more than one level in the region tree to do it, but
I see.
yeah,
Yeah, okay, that's what I was.
I'm gonna leave. I'll leave that as an exercise to you guys to think about. But if you can't figure it out, you just let me know, and I'll give you an example. But yeah, effectively, it's possible to construct these projection trees, effectively in such a way that different shards. I mean, the interesting thing about these is that you have incomplete information, right? So effectively, like, about your local children, right? And you have a detailed view of the tree of your local children. But, effectively, the thing that's interesting about this is that this only summarizes, there is some user down here in this subtree. What you don't know is, like, down the subtree, there might be other shards that have, if this subtree were like, more than one level.
Oh, it's a fence. Oh, it's a fence between shards. It's not like a barrier, like where every shard is. Okay.
Yeah,
Okay.
there's no barrier here. But like, effectively, you don't know what other shards are doing down here in this subtree.
Right.
Right. And so you can have one shard that's actually going to conclude that, it doesn't have any interferences with anything over here, whereas two other shards might conclude that they're both using the same thing in this subtree. And so it's possible for different shards to come to different conclusions about testing these two index-based task launches about whether a fence is needed. Right. And therefore you need the all reduce in order to make sure that all the shards are on the same page. Right? Because the fence is effectively we like I said, I haven't found the need to like actually go to point dependencies yet. There's some cases where the Q-numeric folks want me to do that for Legion, and we probably will do that with these projection functions in some limited cases. But in general, we don't hook up point-to-point mapping dependencies between the index-based task launches at the moment. We just stick in one of these fences between the index-based task launches, and we do that across all the shards globally. So we do need the all reduce.
That makes sense.
Yep.
That makes sense.
So yeah, see if you can figure out a case where, effectively, and you probably need more than two shards, by the way. You'll probably need a few. You'll need a few shards, probably at least three.
Right.
But like, it's possible to construct, an example where two of the shards will conclude that they are interfering with each other, while the third one concludes that it doesn't interfere with either of the other two, and therefore, they come to different conclusions about needing a fence or not.
Right.
Yep.
Yeah, that makes sense.
Yep.
That makes sense.
Okay. Any last questions before we wrap up for today?
I'm good.
Okay, so next time we'll actually try to look at how these data structures these projection trees actually get constructed, and then maybe some other parts of the logical analysis, or maybe we'll have a realm talk. We'll see if I can get somebody to do that as well. All right, talk to you guys next week.